All right, these are going to be our lab notebook pages for lab 20. We're doing rotational motion with a modified Atwood. The objective of the lab is to be able to find the moment of inertia of our rotating disc. This is my setup. I have my lab table, and I have a hanging mass that is in a pulley system. So my modified Atwood is this part here. And when I do collect the lab data, I'll show you what this thing really looks like. But we have a disc that sits on top of some smaller discs. So our string for our Atwood goes on the smaller disc, and we're calculating the bigger disc's moment of inertia. So anyway, there's only a few things that we're collecting data for here. We need the height from our hanging mass to our floor. We need the radius for our inside where our string is pulling and making our set of discs rotate. We also need to know what the mass of our hanging mass is, and we're going to be measuring the time it takes to go our hanging mass from its certain height to the floor. So this Y is going to be the same for each trial. It's something you can decide yourself. So things we're calculating, we are not measuring so much, but we are going to be calculating quite a bit of things. So we want our moment of inertia of our big disc, and we need to find all these other things in between. So I called these smaller discs axis pulleys. It's not really a pulley, but I don't know what else to call it. It's not a disc. I looked in the manual. I couldn't find the name of it. So we're just calling it an axis pulley. This right here, where my string is attached to the thing that rotates. Again, I'll show you this in the video for when we collect the data. So we're going to find our acceleration of our hanging mass, right, using our linear values, our sum of forces. So we're going to find our acceleration using a kinematic because we have a time and a displacement. And we can figure out what this mass is accelerating with linearly. And then we can tie that back to our angular acceleration of the pulley here. We're going to calculate the torque exerted to get this thing rotating. And then the last thing we're going to do is calculate our moment of inertia for the big mass. So we're going to just set it up the way it is in the diagram and time how long it takes to go a distance. A few times, call it a day. This is all of our data. So we need the mass, we need our height, and the radius where our string is, and again, I'll show that to you. Our trials, and we're going to use our average time. Things that we are calculating, all these things. We're going to draw a free body diagram of our hanging mass and write our sum of forces. We are going to write our sum of torques along the axis pulley, right? The torque is being caused by our tension in our rope. We're also going to find our acceleration using our kinematics. We have our height and our time, and our initial velocity of our system is 0. So you can solve for your acceleration. We're going to solve for the tension in the string, the torque that the string provides using the radius r that we measured at the beginning. We're going to solve for our angular acceleration of the axis pulley. And I'll show you too that the pulley and our large disc are going to be rotating with the same angular acceleration because they have the same center rod that they're rotating around. And I'll show you what that looks like when we collect our data. I have what the moment of inertia is of our disc, so once you calculate it yourself, we're going to find the percent error between the true value, which I can give you, and the calculated value you did with your calculations. Finally, tying it back to some graphs, which we haven't done in a while, you're going to sketch for me the angular displacement, angular velocity, angular acceleration for the disc. And for the hanging mask, you are going to sketch me a displacement time graph, velocity time graph, and acceleration time graph.